Okay.
Yeah, just speak a bit louder.
Okay. Hello, everyone. We are Group 12, and our group project is distributed and decentralized machine learning framework. And I'm Huaifeng, and this is Hantang from Umia University, and this is Derek and Qi. We are both, all three of us are from Chinese University. And firstly, I will start this presentation by introducing the outline of the presentation. So we developed the distributed and with some experimental decentralized feature of machine learning framework. And firstly, we're going to introduce some core algorithms about this framework. And then we're going to introduce the distributed part. After that, that is the decentralized part. In the decentralized part, we are going to do a live demo so that you can also participate in this demo. And finally, we are going to do some security analysis of this decentralized feature. And first of all, so to join the decentralized network, actually, we have some preparations work to do. If you are interested in this, you can follow the instructions here. If you are using Mac, you basically you use this command to set the image you want to pull. If you are using Windows or Linux, this is the image you want to pull. And when you pull the image, after that, you run the image to generate an account in your machine. That account will be used to transfer the reward to your account, and you will get rewarded by performing some proof of useful work. So you will get some address. You get an address like this, and after that, you can start the miner on your machine. Basically, this miner will perform some computing tasks, which is submitted by our machine learning framework. And once you finish the workload, you will get some reward. If you are interested, you can basically run this command on your machine, and more detailed ones are listed in this GitHub repo. That is GZ18 NeedleDDD, and you find the final project report here. Yeah, that's just some preparations work. And if you are interested, you can use it. And now let's start the presentation, and I will hand over this part to Hantang, introduce the core algorithm part.
Yeah, so I will introduce the core algorithms using our project. So if you want to build up the framework, you have to figure out what, let's see here, you have to figure out what algorithm to use. So we investigate, compared some basic algorithm, and then we, so in our project, we have two main algorithms. One is we call AutoDiff. So this is a stand for the automatic differentiation. It's a computational technique, and we compared this one, numeric differentiation, and the another one, symbolic differentiation, and we decided the AutoDiff is the best core algorithm we can use. And how in terms of the how AutoDiff works, it worked in two modes. One is forward mode, so it tracked the derivatives as the computational progress from the input and outputs, and also the back propagation. And so the role of the AutoDiff in our project in the training neural networks and the optimization. And why we choose that? Because in terms of the accuracy, compared to some numeric differentiation, it can help us eliminate the errors, and also it can make sure the efficiency and the flexibility. So in this part, to sum up, the AutoDiff provides it's a useful tool in both the training process and the optimization. And another algorithm is GMM, short for the general metric to metric multiplication. And I know it's a key algorithm in basic linear algebra subprograms. So, and I think most of you guys know this. And so how GMM works, it works in block multiplication. So then this can fit into the memory. And also it can make sure the parallel execution and optimize and also can optimize the memory access. And the role of GMM in our project is include the three parts in the neural network operations and the back propagation, and also it can make sure the model training efficiency. So the benefits of the GM in our project is so first is the performance. It can make sure the hardware can make sure in terms of the hardware can reduce the computation time, and also and can also make sure the scalability and robustness. So GMN is, I would say, is indispensable in our project. It powers the core metrics operation needed for efficient neural network training, and so it can make sure our framework is state of the art computational efficiency. So then the Qi gonna introduce the distributed machine learning.
Yes, our framework supports the data parallelism and also the model parallelism. So the first part, it is the data parallelism. And here we just split the train data into different partitions and allocate the data into different nodes. And then this is the formula of how to calculate the loss function, and depends on the data partitioned to the node. Yes. This part, I think it has been introduced by group 7 in the morning. So yes. So we also use the or reduce to update the weight. We show a lot of code or logs or logs here. Yes. Yes, here we train a very simple network, just ResNet. And here it is how we implement it. The first, it is after we define the ResNet, import the ResNet, then the first part, it is the broadcast parameter. It will broadcast all the parameter to all the nodes. And then they also design a distributed optimizer. So here it do the all reduce work. It will update all the weights on different nodes of the GPU. Yeah. So here it is the performance of if we train on 4 GPU. The training time, it is like this. And then this is with single GPU. So the performance, it is just, yes, here the above this block, this log, it is run on 4 GPU and this on 1 GPU. So we reduce like 70% of the training time. And this is how we implement the data partition. The data partition, it will divide the data set into multi-partitions and transfer to different nodes. This is the broadcast parameter. And then the distributed optimizer. The distributed optimizer did the work of the all reduce. So it will aggregate the gradients calculated by each node. Yes, but it's good that this part has been introduced by group 7 in the morning. So I can save some time here. Yes. Oh, I can. So here it is the model parallel training part. So here on different GPU, if the model is too complex or have a large of the parameters, if one GPU cannot hold all the memory, so we usually meet the out of memory problem. Here we can split the model on different GPU. So for GPU 0, it can just calculate layer 1 or 2, layer 1 to 2, and then GPU 1, it calculates the other parts of layer. So for the data parallelism, it split the data onto different nodes. And for this model parallel training, we split the model onto different GPU. But there is a cost here. It has to pass the intermediate result between GPU. So after this layer 1 after this layer second, it finished the computation. It has to forward the intermediate result to GPU1 and do the forward pass. And also in the backward pass, it also has to backward the gradient or the intermediate result to other layers. So there is a lot of the overhead of the communication cost here. And this is just the prototype. And after our optimization, the training time goes back to just one GPU. Yes. So the time is longer compared to data parallel training. Yes, if you look at this flow, you can see that with the layer 3 and 4, they have to wait until the layer 1 and 2 finish the calculation of all the data or all the data in this batch. So there could be an optimization after layer 1 or 2 finish the micro batch, just finish part of the data, then it can forward the result into layers 3 or 4. Yes, so here we do the data pipeline model parallel training. So we split the data set into different parts, and it can forward the data earlier. So we wish this to reduce some overhead of the serialization of data training. And maybe the cost of the communication is still very high, and the training time is even longer at this time. Yes. And yes, the problem may be that we train on the Alvas cluster, and with the default GPU, we train on Tesla T4. So maybe if we use A100 and use the NVLink, it could be better. Yes, this will be the to-do work.
Now it's the decentralized part. Before I started this part, I want to ask, like, how many people has started the client? Nevertheless, I will start my own client to run this demo. So first is how we design this decentralized machine learning, and I want to clarify that this is a very simplified version of this decentralized machine learning. So in practice, actually, there's a lot of other concerns that we need to think about, like security, privacy, and fault tolerance. This would be a minimum viability prototype. That is, if you want a decentralized machine learning framework, this is the minimum element you need to include it in your system. So our decentralized machine learning framework includes two components. So the first component is the machine learning framework. We call it the Needle framework, which is basically we just introduced before. It's just a PyTorch-like framework. You use this framework to write to define model, to train the model, to deploy the model, and you just use it like PyTorch or TensorFlow. And this is the first client, and the second client is what we call the Go Needle client. Actually, this is the network client. It means users use this client to join the open network to provide their computing resources, so that the users who use the machine learning framework could use these resources. Here is the overview of the structure. So firstly, there's user A. He writes some code based on the Needle framework. This is the first client of our system. He writes some code, like define some models and train it. Underlying the Needle framework, the machine learning framework will package the code, or will package the code into a transaction. The transaction basically includes two parts. The first part is the computational graph. Basically, the machine learning model you define is actually a computational graph. And the second part of this transaction is the parameters. So basically, the weight. And this transaction will be submitted to the decentralized computing network. This decentralized computing network is created by the network client, which is the second component of our system. Basically, all our users can join the network permissionlessly. I mean, it's an open network, so you can join the network to provide your computer resources. And this transaction will be executed on one of these nodes in this network. And the result will be packaged into a block. And yeah, basically the block will have some transaction hash. Basically the block includes the result. So this is the basic architecture. So the machine learning client called Needle, it's this part. And the network client is this part. And yeah, here's some detailed design or conceptual design of this, what is a transaction. So here we show an example of the transaction. Basically, this is an example of a transaction. The transaction first, it has the submit address. That's the user who submits their machine learning workloads to this network. And this is their address. And another field is data. You know, it's just just the parameters of the models they define. And also this ops is basically the computational graph. And I guess this is okay. How much money do you want to pay for this for your workload? This is the Needle framework or the machine learning framework. And we have another client is the GoNeedle client. This is the client to join the network. And so in this decentralized network, there are actually two types of node. The first type of node is miner, which basically perform the workload which is submitted by some other users. And the miner, the verifier, they verifies the result of the miner to make sure the result is correct and to make sure the miner, they work honestly. Or else they can, you know, without verifier, the miners can just output some random result. So we cannot verify it. That is actually harmful to the network. And yeah, also in our protocol, we don't require how miners could compute the result. So the only responsibility of the miners is to generate the block which includes the result. So they can use different ways to compute the results. They can use GPUs, TPUs. They can use distributed computing. They can use federated learning, whatever. So we only require they should generate the correct block. So this is what a block looks like. The block first has the miner, which means who generated the block, who computed the result. And then transactions. Transactions, it's basically, okay, how many transactions do you compute in this block? And also, because they say borrow some concepts from blockchain, so we also have the hash of the parent block. Yeah, and I think the most interesting or most challenging part for this kind of decentralized network is that how do you verify the result? We propose 3 potential ways to do this. So the first way is use some mathematical way or algorithmic way. For example, for the matrix multiplication, usually if the miner compute the matrix multiplication, the time complexity is kind of shows here like this kind of what do you say that? This kind of quite complex actually. But we find some like algorithm called favored algorithm that we can verify the result actually in a kind of cheaper way. Instead of computing the result, we kind of a quadratic time complexity with a small probability error. It means so that the verifiers can verify the result to reduce the probability of the error. And so this gives us some sort of proof of work style to verify the result. So this is the first way. The second way is that we think we can also use some challenging way. It means that some verifiers, they will issue random computing tasks to the miner. So the miner and the verifiers know the result in advance. So they will check whether the miner is working honestly to get the result of this challenging task. But the problem of this one is that sometimes maybe the miners, they could identify the pattern of these challenging tasks, and they only perform honestly when they receive the challenging tasks. And when they receive the tasks from the random users, they just cheat. And another thing is, another way is that maybe you can use some voting mechanism. Is that this computational task can be distributed by multiple miners, and the result is considered correct if the majority of the miners have the similar result. But this problem is that apparently it wastes a lot of resources. So basically, this is a quite a challenging and interesting problem. Like the first way, I even doubt that if there exists some algorithms that we can prove the result mathematically. So this is quite a challenge. But for our demo, we only use this Revolt algorithm to verify the matrix multiplication result. And yeah, here we also have a demo. So to have the demo, first you need to set up the network, which I have already kind of introduced in the at the beginning of this presentation. So you download the client network client and you run it on your machine. Then this client will join the network, and to use the network, it means you need to write some machine learning models to submit these machine learning models to the network. First, you need to have an account address, and yeah, it's kind of a kind of private key. It's some just setup environment setup, and yeah, here we can actually check. This is my account address. I'm the user. I want to submit a task to this decentralized network. And to submit a task, first I need to pay for my workload. So I need to have some balance in my account. So if you check this one, you can say, okay, I have some balance. So I can submit my machine learning task to this network. And here I basically define a super easy, super simple computational workload. This is just a matrix multiplication. Basically, we define a matrix A and a matrix B. Then we call this decentralized operations, which is decentralized matrix multiplication in our framework, and submit to the task. If you say this will generate a hash of this transaction, basically this will the framework the machine learning framework will package this one as a transaction and submit it to the network, and this task will be executed on some nodes in the network, and we can get the results to see the results. This result is actually computed by some other nodes, and the nodes package the result into block, and the machine learning framework just query the block to get the result. We can see how this block looks like. You see, here we find the block according to the transaction hash. We can find that this block is actually generated by this miner. This miner is it means this miner performs this computational workload, and because this miner did this, and this miner will also get the reward. So we can check the balance of these miners. If we check this miner balance, we can see it did get some reward because it performed this useful work. And me as the submitter, my balance is reduced because I submitted some workloads to this network, so it uses my money. And there's also some consideration that's quite interesting for this one. So firstly, the efficiency is a big problem in such a decentralized network, because for those, some machine learning models, computational networks, computational tasks, they can have a large set of parameters. So a lot of time are needed to transfer the data between the users, miners, and the decentralized storage. So this is kind of a big problem. And also the privacy is another problem, because the data, can be actually private. So the user might not want to share this with others. Also, this can cause centralization problem, because some big complex tasks that require a lot of computing resources that can only be computed by a few miners with powerful resources. So which is so in this way, this is not decentralized at all. And the reward mechanism is also quite interesting. So So the reward should be based on the computational complexity, such as flops or other concerns. And also the real time a miner spends on the computation should also be considered, because as a user, you should expect a faster response of your result, of your task. So a short time should also get a higher reward, but this is kind of also can be a quite interesting problem to explore. And then the final concern is that economic consideration. So in such a network, the amount of the rewards keep increasing, so which might lead to the inflation of the network. And this inflation can disincentivize the miners to join the network, and eventually leads to the failure of the network. So yeah, I would say this is just a prototype of exploration of such a decentralized network. And yeah, there can be many issues that need to be fixed. One of the biggest issue is the security of the decentralized machine learning. And this is Eric's task.
Yeah, so I was looking at this. Hopefully that survived. Yeah. Okay. Yeah. Looking at the security of an abstract version of this sort of decentralized machine learning scheme. So it disagrees in some of the small details with what he just presented, but we'll sort of disregard a lot of that. So first of all, in this analysis, I'll be assuming that the data is available in some sort of distributed store already, and that is assumed to be public. So this is a big assumption, right? But otherwise, it's very similar to a scheme. So where a user sends a task to the network, the miners in the network solve this task, and they receive a reward upon success. We can build some security properties for this scheme, because this was sort of a very ambitious goal to have a fully decentralized network where the miners have zero trust in the user and vice versa. So I guess going from bottom up, we first want to ensure that the miners actually get paid for doing work, so we get fair payment. We also want model privacy, because somebody's paying for this model to be computed, so it seems likely that they also want it to be theirs and therefore private. And we also want actual computation to be done. So the user does not trust the miners, and the miners have to actually somehow compute the task rather than sending noise or rebroadcasting some prior result. There's some relevant areas we can steal from, ideas from, which is what I do exactly. So data marketplaces, decentralized federated learning, and what we're actually approaching here, which is decentralized machine learning. So if you look at federated learning specifically, these are some diagrams from a centralized federating learning thread analysis paper, and there's a bunch of attacks possible everywhere, not all of which is relevant here because we're not considering data to be private. So that actually eliminates a lot. But some that are still relevant are what they describe as business attacks at the local worker. Model poisoning is also relevant, but I'm just not going to consider that because that's basically unsolved in the federated learning world. And so it's definitely not solved in this more general case we're approaching now. And then also this model extraction attack. So some mechanisms that are being used in federated learning to protect against these I can reuse. So to look at some specific papers that try to achieve decentralized federated learning or machine learning, we can look at how they've used some of these tools. So in this chain FL work from 2020, then they use a blockchain like us. They chunk this data onto the network so that it fits on the blockchain. And then per chunk, they assign smart contracts, which with proof of authority, so if you pass some test data set with the sort of computation you've done, then it gets put onto the blockchain. And then they accumulate results with online federated averaging. So this is some step towards the right direction. We have these smart contracts that at least ensure that we are getting payment for work, and we also have this proof of authority, which does a little bit of a basic check that the computation is actually being done. However, even in this paper, they acknowledge problems with still that this Byzantine updates is not being solved because this federated averaging is basically broken when we want to consider multiple malicious users, because if you have one very malicious result, it can skew the whole average very badly. And also we have the whole global model being shared on this network, so it is essentially public. Some other work also use blockchain, blah, blah, but they have some differences in the specifics. Yeah, we can describe this one. This is the one that's most specific to what our model is doing, because in their threat model, they're covering both model privacy, data privacy, and resistance to Byzantine data owners. So that'll be the mining nodes in this instance, as well as the model owner, so us paying for our tasks to be done. And they achieve this by first splitting the model. So similar to how, like with an LLM, you're generally training the final layers and you're keeping the rest private. This is what we'll do in this setting. So we'll only distribute the final couple layers weights onto this network to be trained. And then it's being distributed to these individual data owners. So we can imagine that they hold some segment of our public data. And then they're solving this smart contract, which hold parts of its task. This basically is using a few solutions from federated learning, where we're having this private public model splitting to get the model to not be public anymore, or at least all of it. We're using blockchain and smart contracts to ensure payment. We're using secure aggregation, basically multi-party computing, to again ensure data privacy, but also a little bit about model privacy. And we're using multi-crumb, which is this bit up here, to try to get away from these Byzantine model updates. So ones that deviate very strongly from the normal case will just be thrown away and not rewarded in this network, moreover, by a smart contract. Yeah, I won't really get into problems, but yeah, it's unconvincing that it actually does solve the problem. It maybe defends against the most basic attacker, but you will need a lot of work to solve this very ambitious problem. There's a bunch of next steps. Yeah, eager to answer any questions.
Towards the Byzantines.
I don't know, that's just the name for it. It's non-consensus reaching updates is another way to describe it. Byzantine.
I mean, the etymological, it has something to do with the way Western Roman Empire interprets the Eastern. I don't know.
It's like a standard term in distributed computing.
So this gas that you had,
Yeah.
I mean, that's basically how you keep track of it's like your money, basically, right?
Yes. Yes. So, I mean, I think this gas shouldn't be provided by the user, by the submitter. It actually should be kind of calculated by the framework or the network level. It should be estimated automatically, like how many flops of this task, and it should be priced according to these flops. Yeah, it shouldn't be provided by the user, because I developed this based on some existing, blockchain clients, so kind of compatible with those blockchain clients.
I've just been recently interested in economics over the last year and a half or so. So, like, let's say you introduce another monetary concept here, right?
Yeah.
Because at the end of the day, there are some users, some miners, but then in the end, the model gets created. Right?
Yeah.
And of course, there are going to be users of that model who will pay some gas.
Yeah.
When they're happy with its results, right?
Yes.
So the whole system becomes self-sustaining, because when that monetary value for actually using the model flows back to the chain of those who created the model, right?
Oh, yes. Yes.
Yeah.
With federated learning, it's sort of like a complete system because the private data owners have interest in this model being generated. Yeah, but it's harder here because we have some gap outside this.
No, yeah. I'm just thinking like, let's say there is some emergent property of a useful model appearing at some point, right? And then
how this can,
because then maybe the ownership of the model itself can get inverted on like who created it. And then you get like some kind of a fair rent or whatever the model used, right?
I think this can just, I think maybe this can be, we can add some programmability of the network, like we can define some kind of smart contract. The user can define some smart contract, so the smart contract can build a new reward mechanism that if this model is used by other users and the developer of this model should get rewarded. I think this can be programmed by some smart contract. I think this is solvable, but from now, for this kind of design, I didn't haven't considered that.
Yeah, I'm just sort of trying to think like what would complete the sort of economic theory of data model commons, with some emergence.
How many verifiers will it be? Is the number of verifiers corresponding to the miners? And do verifiers get rewards? What's the incentive?
Yeah, the incentive should be like this. If the verifiers like find the result, I mean, there are two things actually. So the first way is that the verifier doesn't get an incentive, but this apparently, it's not a good design. The second way is that I think the verifiers, if the verifiers find a malicious block, basically the verifiers should also get a reward because of this. So in such a way, we can incentivize, we can motivate the verifiers to join the network to make the whole network safer. Yeah, but I feel, I mean, this week, this is the way to solve this problem. Actually, I think there's a more like economic concerns about this, because in such a way, actually, we kind of increase many rewards in the network. It kind of, as I said before, it can easily lead to the inflation problem, which basically quite harmful to the whole network environment. But I mean, that's a way to incentivize the verifiers.
That's possible that several clients are working on the same model, but with different batches of data.
I said before, the miners actually is an abstract of the only responsibility of them is to generate the correct block with the correct result. So how do you generate the correct block? How do you generate the result? You can use the distributed learning. I mean, you can compute this on multiple GPUs, on multiple machines. You can use the another decentralized machine learning, as you said before. You can use the federated learning. So it doesn't matter as long as you generate the correct block. Yeah, that's the only.
But there could be many. I mean, each clients are just working on just one step of the update.
Yeah, I mean, in the network we have nodes, right? These nodes, one node only compute one task, and how the task is computed, it doesn't matter. You can split the task into different machines. Yeah, but it's not this problem is not tackled at the network level. It's tackled by how miner implement their computing function.
Yeah, this is only like a basic implementation. It doesn't support. I think
you can think of this network kind of like a resource management system. Actually, it doesn't define how the miners compute the task. You can implement in your own way.
But I mean, there are several ways to several correct ways to compute the updates
Yeah.
by selecting different batches statements. Then how do you handle that?
I mean, this is handled by the node. So if you are the node provider, right? You want to compute the gradient. You don't want to update the node in that way. Then you implement your computing function in that way. I mean, the node only generates the block. It doesn't do anything else.
It would be better if we could specify that network. So yeah.
It's more complex.
Okay, no other questions. That's fine.